Let's talk about the regularized attack. In this half of the lecture, I'm going to talk about the third form of adversarial attack. And in this regularized attack, as you can see from the name, it will be an optimization problem that does not contain a constraint. Everything is written in terms of the regularization. I'm going to talk about the linear case, and then I'm going to talk about one type of deep neural network attack. It's called the Carnevy-Wagner attack. Let us first try to understand this regularized attack from a two-class linear classifier setting. So as you can imagine, in the max loss attack and also the minimum distance attack, you will have an objective function and then there is a constraint. In the regularized attack, we are going to put everything into the objective function. So in this case, you have the objective function of x minus x0 2-norm square. And then you have all the constraints put together in the form of a penalty function. And so here there's a lambda. The lambda is the optimization. There's a regularization parameter which you can tune to make it bigger or smaller so that you can control how much you want to rely on the constraint or not. If you restrict yourself to two-class linear classifier, then this problem can be simplified to the following, where you can replace this max by just the GJ because you're only looking at two class. And then you're only looking at the linear classifier, and therefore you have the W transpose X and WT0, and here you have the WJ transpose and WJ0. And therefore, you can combine the WJ and the WTs into one W and WJ0, WT0 into one W0. And so the optimization problem will look like this. And this is the regularized attack for two-class linear classifier setting. This is an unconstrained linearization, and we are very happy about this formulation because you can just take the gradient of this objective function and set it to 0, then you can get to the solution. And specifically, if you let phi to be this objective function, you take the gradient of phi, you will get to this form, and therefore you will have the solution being a gradient of phi x, which is the gradient of the 2-norm square of this term, which is x minus x0 plus lambda of the gradient of this one, which is w. And so if you set it to 0, then your solution will become x equals to x0 minus lambda of w. So the solution is very simple. And so we can pretty much conclude the regularized attack in this single slide. So if you have a regularized attack for the two-class linear classifier, then the solution is nothing but just this very simple equation of x equals to x0 minus lambda times the w. And w here would certainly be your search direction, and lambda would be your step size. And you need to choose a good lambda. Same as the maximum loss attack, you need to choose an eta. So you need to choose a lambda in order to find the right step size. If your lambda is too big, then you will overshoot. If your lambda is too small, then you may not be able to go into the wrong class. And so this lambda has to be carefully tuned. Now, the L2 form of the attack is a very, very easy problem, which we can summarize everything in one slide. How about we change the attack to a L1 norm type of attack? Then we suddenly realize a problem that this optimization problem actually becomes a lot harder. So let me explain. In the regularized attack, why is the attack significantly harder when you change the norm to a 1 norm? So let's consider this L1 norm case where the objective function contains the L1 norm of the perturbation strength, and then you have the constraint here. Now, this is the same as if I just replace R equals to x minus x0, then this is your optimization problem. And so if you try to take the gradient setting it to 0, then you can more or less sort of argue that you can take the gradient, actually has to be subgradient of R1, then you will get a sign of Ri plus lambda of Wi. That has to be true for all the i's. Okay, so this really requires you to have that this lambda times the wi has to be either plus or minus 1, because this equation says that lambda of wi has to be equal to minus of the sine of ri. This is the solution that you will get from the optimum point. Okay, so you take the gradient, you get to the optimum point. That would be a condition that you must satisfy. And therefore, if you have this equation here, then lambda of wi will either be plus 1 or minus 1, depending on the sign of the r. And so as long as the absolute value of r is positive, that means as long as your r is not 0, you will either get plus 1 or minus 1. Now, if your r is actually 0, then you can show that by the definition of subgradient, then this lambda times wi has to be a number between minus 1 and 1. And therefore, if you put an absolute value here, then that means your lambda times wi will never exceed 1 for whatever r that you're choosing. So this is the optimum point, but we know that this lambda is something that the user can choose. The w is the classifier's parameter. So as soon as the lambda and the w's are defined, then you do not have any freedom of choosing them. And so if for some specific choice of lambda and w, this number is bigger than 1, then this above optimization is impossible to hold, regardless how we choose the r. So in other words, that this objective function may not reach a minimum point by just choosing an r. No matter what r you choose, you will never satisfy this optimization criteria. So what does it mean? Well, it means that your optimization may or may not even have a solution for this problem. And this can happen because you look at this function here. This is the L1 norm of your optimization variable plus another linear term here. This number can actually go to minus infinity as your x goes to minus infinity, if your alpha is bigger than 1. Okay, and if your alpha is bigger than minus 1, then x can go to plus infinity, and so the solution will go to minus infinity. And so what it means is that this is really unbounded below, and therefore you may not have a solution. And so if we go back to the problem here, this is the L1 norm in the form of the regularized attack. And this very simple change from the L2 norm square to L1 norm will suddenly make this problem not solvable. So what people have observed is that we need to do some additional trick if you want to handle all these problems. And this trick is also generalizable even if you replace the L1 norm to other types of norms. So this is the Canlini-Wagner attack that was proposed in 2016. The idea is to put a max operation in the constraint. So what do we see here? We are seeing that this is the original constraint, and then we are saying that as long as this constraint is bigger than 0, we're going to keep that. Otherwise, if this is less than 0, I'm going to throw it to 0. So what is the intuition behind this setting? Well, if this is less than 0, then it's already misclassified, and so you do not really need to do any further action. However, if this number is positive, then it is not yet misclassified, and therefore you do want to perturb it until it is misclassified. And so here we can introduce a function that can summarize this max of x and 0, this kind of operation. I'm going to define a function called the zeta. The zeta x is defined as max of x and 0. That's also called the rectifier function. And so the problem can be written as this norm of the perturbation strength times lambda times this zeta function applied to my constraint. And so this norm here says that it can be either doing L1 norm or L2 norm or any other forms of norms. So we can compare the regularized attack and also the minimum distance attack, and you can see that it's the same objective function. However, in the regularized attack, I'm using this rectifier on this constraint. In the minimum distance attack, this function I of omega, that's an indicator function, is either 0 or plus infinity. It is 0 when the constraint is negative, and it is plus infinity for otherwise. And so the idea here is that the regularized attack is really a soft version of the minimum distance attack, if you want to put it this way. So we can apply this soft attack idea into the L1 norm, and we can see that why this can solve the L1 norm issue. So you can apply this rectifier function, max of this term W transpose X plus W0, and then there's a 0 here. Then you can show that the objective function is always non-negative, because this is non-negative and this is also non-negative. And therefore, we are guaranteed to have a solution, because if this is non-negative, this term is also non-negative, and you're doing a minimization problem, then certainly you can really get to the minimum point. And what is the minimum point? The minimum value here has to be 0. Now, if you really can reach 0, then certainly this optimization problem can be solved. But even you cannot reach 0, this optimization problem in principle is bounded below, and so you will be able to find a solution. Now, here is a trivial solution. It's a solution which can make this objective function really exactly equal to 0. So what is the solution? The solution is that you can make this thing into 0, and then you can make this thing into 0 as well. So when will this happen? It happens when x equals to x0, and also the constraint is completely satisfied. Now, this will happen when your attack solution, this x is 0, is actually right on the decision boundary. Then you can show that this solution will actually go to 0. Now, of course, if your x0 is not even on this decision boundary, you can still do the attack. I can still guarantee you the existence of the solution. It's just that the solution will not give you a 0 objective value. Okay, so in addition to this L1 property, we can also show that this rectifier function is convex in terms of x, as long as this function of phi is convex. Now, what is this phi here? This phi of x is, of course, our linear constraint. This is a W transpose x plus W0. This is a linear term, and so it is convex. What we can also show is that this rectifier function is also convex. Now, how do we do that? You can just follow this very simple recipe type of argument, that you pick any 2 points of x and y, and then you define a variable scalar alpha between 0 and 1. Then you can plug in the definition of this rectifier function by doing this a sequence of inequalities. The first inequality says that since this is convex inside, then the convexity will come out for the first inequality. Then the second inequality says that you are doing a pointwise maximum, and therefore the pointwise maximum has to be bigger, has to be convex. So this is one of the properties in the convex optimization literature, which says that if it is a pointwise maximum operation, then it will remain a convex function. So that would be the second inequality, and then you can just apply the definition to get back those rectifier functions, and you can show that it's convex. So what is the implication here? The implication here is that here is the rectifier function, and then here it is a linear function, and therefore the entire term, this term, it is a convex function in x, and therefore this problem is a convex function, and so you can solve using any convex solver, for example, the CEX. So now let us move on and talk about how do we generalize this regularized attack to deep neural networks. In order to attack this problem in the deep neural network setting, we are going to assume a very general G, meaning that we do not just have a linear classifier, but this G can be a deep neural network. Now, I also want to keep this zeta function here because it is really the soft version of my constraint. And because of this rectifier function, this rectifier function actually has this shape of being a 0 everywhere, and then you have a slope 1 a function. That is your zeta of x. Okay. Now, if you take the derivative of this zeta, then you can see that it has to be 0 everywhere until when you hit 1, then you hit 0, then it becomes a 1. So this is the gradient of the zeta. And so you can show that if you take the gradient of this function, you will be able to get some kind of gradient, which is just the indicator function of whether your s is bigger than 0 or not. And so what we can do now is trying to handle this maximum operation. This maximum operation can be handled using a heuristic, which says that I'm going to evaluate my discriminant function gj, and I'm going to pick the one that can maximize this discriminant function. And then it will be index I that among all the discriminant functions gj's, I'm going to pick one I star that can maximize it. So for the time being, let's assume that this index xi is independent of my x. And so I can show that the gradient is this. So you can show that if you take the gradient with respect to x on this zeta function, then it would be the gradient of this zeta of this term here. Now I will replace this max by this I star because I'm picking really the I star index of this discriminant function. And then I can evaluate this gradient. The gradient will say that it's either 1 or 0. Now, if it is 1, then I will keep this term because I also have the chain rule going on here. If you remember, this is a gradient of x of the psi of some function of x. Then, of course, it has to be equal to the gradient of this psi times the gradient of g. Because there will be there's a chain rule going on here, and therefore you will have this gradient of x of I star minus the gradient of gt with the constraint that this is positive. And so what you can do now is really to combine this pair of cases into one single equation and say that this is the quantity I want, and then I will go to put the indicator function that will come out from this constraint. So constraint says that as long as it's positive, I'm going to give you a 1 according to this indicator function, and then I'm going to multiply with your gradient. Then that will be the ultimate gradient that I'm getting. If this is negative, then I'll go to the 0 case, and that's fine because the indicator function will give you 0, and so the overall gradient will become 0. And so what it means is that you have this objective function, then you have this 2 norm square as your objective plus this constraint here. Now you want to solve this problem using an iterative algorithm because of course G is a deep neural network. You cannot just get a closed form solution from that. So you're going to run the gradient descent algorithm, and then the gradient descent will take this form. When you have gradient, you need to take this gradient of your phi function, and it will be this plus anything else that you can compute from your gradient. And so this gradient is actually very computable in a sense that this is just the deep neural network evaluated for this decision boundary, same for this guy, and these can all be computed using the backpropagation approach. So here is the Carnevy-Wagner attack approach, which says that you are going to run in the algorithm for k iterations, and then during the k iteration, the first thing we do is to pick the index that can give you the maximum discriminant function values. Now you can do that by just sending an image through the network, and then you can ask which class is the most likely class, and then you pick this index I, and then you plug it into this gradient function. And then you evaluate this gradient. And once you have evaluated the gradient, you make a gradient descent step, and then you make an update. Then you go back and forth. So this is a CW attack, and here is the comparison between various attacks. So here is the FGSM. This is the IFGSM. this is the deep full attack, and this is the Kalini-Wagner attack. So you can see that in these images, the behavior of all these attacks, they are similar. Now that shouldn't be a very big surprise, because all these attacks, they are coming from 3 different forms of optimization, and therefore their behavior should be similar. Now certainly, this FGSM is a one-step attack, and so compared to IFGSM, which is an iterative attack, the iterative version will certainly be stronger. So is the Kalini-Wagner attack. And so if you look into papers like these, they will show you the comparison between all these attacks by using the fixed amount of perturbation step size and how much error that it can create. So I encourage you to take a look at papers like these and get a better sense of the strength and also the weakness of all these attacks. So to wrap up, we have introduced 3 forms of adversarial attacks over the past 2 lectures. We have talked about the minimum distance attack, we talked about the maximum loss attack, and we have also talked about the regularized attacks. So starting from the next lecture, what we are going to do is to talk about defense, because we have studied 3 different forms of attacks, and then in each form of attack, we have introduced the attacks in the deep neural network settings. So I think everyone is now very excited of trying to attack your own model. And so what we are going to do next time is to also talk about the defense strategies. Now, after we talk about the defense strategy, we also want to spend 1 lecture to talk about some very theoretical problems of what is the fundamental trade-off between robustness and also accuracy of a classifier. Okay, so thank you for staying with us, and I will see you next time on the internet.